Hello, and welcome to Boring Science for Sleep. Here, science is told slowly, not to wake you up, but to guide you gently toward rest. Tonight, we're going to wander into a question that feels both simple and endless. Does time flow the same everywhere? We live by clocks, by the ticking hands and glowing numbers that slice our days into hours, our hours into minutes, our minutes into seconds. But is that time the same for everyone, everywhere? Or does it stretch, bend, and ripple quietly beyond our noticing? We'll drift through mountains and valleys, through the stillness of space and the pull of gravity, and we'll find that time, like a slow river, can flow differently depending on where you stand. If you enjoy these soft science journeys, remember to subscribe so you don't miss the next quiet adventure. And tell me in the comments, what time is it where you are right now? And how does your night feel? So, settle in. Let the clock tick on somewhere in the background. And together, let's see where time takes us. Before we could ask whether time flows the same everywhere, we first had to believe in the idea that it could be measured at all. And for most of human history, time wasn't something we carried in our pockets or checked on glowing screens. It was something we felt on our skin, in the warmth of sunlight, in the stretch of a shadow, in the steady rhythm of our own heartbeat. Early humans didn't have hours and minutes. They had mornings and evenings. They had the slow curve of the sun across the sky. They knew the difference between the long, gentle light of summer and the short, sharp daylight of winter. Time was the cycle of seasons, the return of the rains, the ripening of fruit. It was not yet a number. It was a story told by the world around them. At some point, our ancestors began to notice that shadows were not only longer or shorter depending on the season, but also stretched and shrank in a predictable way through the day itself. A stick placed in the ground became a primitive clock, its shadow creeping along the Earth's surface in a silent arc. This was the sundial, a way to carve the day into slices, not by sound, but by light. The sundial was beautiful but imperfect. It told time only when the sky was clear, only in the daytime. At night, time returned to the stars. Our ancestors learned to watch the sky's slow rotation, to follow the constellations as they wheeled overhead. The position of certain bright stars could tell a sailor whether the night was just beginning or almost over. But humans wanted more precision. We built water clocks, bowls with tiny holes in the bottom, letting water escape drop by drop, measuring time in the steady rhythm of falling liquid. Others used hourglasses, turning sand from one chamber to another, listening to the soft hiss of grains, marking the moments. These were our first steps toward carrying time with us, toward creating a world where we could say, "This meeting will begin in the third hour," and actually mean something to someone far away. Then came the mechanical clock. Springs, gears, pendulums, all working together to divide the day into equal segments. No clouds could hide the time now. No winter storm could stop the hands from moving. Time began to live inside walls, in churches and city towers, its bell ringing out across towns to call workers, to summon worshippers, to signal the closing of markets. For centuries, this was enough. But as the world grew faster, ships crossing oceans, railways linking distant cities, we discovered a problem. Time, once local and personal, wasn't the same from town to town. In one place, the sun might be directly overhead at noon, while in another place, just a short ride away, noon might come minutes earlier or later. We needed standard time, a grid that divided the Earth into zones, each keeping the same clock. That was the 19th century's solution. Time zones, drawn like invisible stripes around the planet. Now trains could run on a schedule, and people in faraway cities could agree. On the moment, something happened. We began to treat time as if it were universal, as if it ticked away identically everywhere. But humans are restless inventors. Even the best pendulum clock drifted a little each day. In the 20th century, we built something better, the atomic clock. It doesn't watch shadows, doesn't listen to water drops, doesn't rely on swinging pendulums. Instead, it measures the vibration of atoms, cesium atoms, to be exact, tiny oscillations that happen billions of times per second, with exquisite regularity. An atomic clock is so steady that it can keep time to within a billionth of a second. With this, we declared victory. We could set a time in one place and trust that it would be exactly the same anywhere else on Earth. But as you'll see in the segments to come, this sense of victory was only an illusion. Time, as Einstein would later whisper to the world, is not the same everywhere. Even now, as you listen, your clock and mine tick together, but they are not truly in perfect agreement. They are shaped by where they are, by the pull of gravity, by how fast they're moving through space. Every time we check our watches, we're making a quiet compromise, pretending the world is simpler than it is. Still, our journey with time measurement is more than a quest for precision. It's also a story of trust. We trust that when we say tomorrow, we mean the same thing. We trust that when a friend says, "I'll meet you at 8," their 8 is the same as ours. Without this trust, our days would unravel into confusion. So, the human clock is not just a machine. It's a shared agreement, a heartbeat we've decided to count together. From shadows in the dirt to vibrations in the heart of an atom, we've been trying to hold time still, long enough to share it. And yet, as we'll soon discover, time has never really been still. It flows, stretches and bends, sometimes gently, sometimes dramatically. And if we listen closely, we can hear it changing, even when our clocks say it hasn't moved at all. For centuries, we imagined time as a perfect river. It flowed in one direction, steady and unchanging, sweeping everything along with it. A second was a second everywhere, in the depths of the ocean, on the peaks of mountains, in the stillness of a desert night. Then, in the early 20th century, a quiet figure began to question that certainty. Albert Einstein, a man with wild hair and patient eyes, suggested something astonishing. Time is not fixed. It bends, it stretches, it can flow at different rates, depending on where you are and how you move. This was the birth of relativity. And though the word might sound complex, its truth is both simple and poetic. Time and space are woven together into something called space-time. They are not separate threads, but parts of the same fabric. When the fabric is stretched, twisted, or curved, both space and time change together. Imagine placing a heavy ball on a trampoline. The surface dips under its weight. If you roll a marble nearby, it curves inward, following the bend in the fabric. Einstein told us that gravity works the same way. Mass bends space-time, and time itself is part of that bending. This means that in places where gravity is stronger, time actually runs more slowly. A clock deep in a valley ticks, a little more gently than one at the top of a mountain. Two identical watches, set perfectly in sync, will disagree if one is kept near the surface of the Earth, while the other is taken high into the atmosphere. The difference might be small, measured in billionths of a second, but it's real, and it's been measured many times. Einstein also whispered something else. Motion itself changes time. If you move very quickly, close to the speed of light, your time slows compared to someone standing still. It's called time dilation, and it means that a traveler racing across space will age more slowly than those they left behind. To the traveler, everything feels normal. Their heart beats at the same pace. Their thoughts drift along as always. But when they return, the world they left will have grown older than they have. This is not science fiction. It's a reality that affects astronauts in space. Moving fast, high above the pull of Earth's gravity, their time ticks differently. The difference is tiny for now. fractions of a second over months, but it's enough that engineers who design satellite systems must correct for it. Without accounting for relativity, the GPS on your phone would lead you miles astray. Einstein's universe is not a rigid stage, where events happen one after another in a strict, universal rhythm. Instead, each observer, each person, each planet, each galaxy has their own clock, their own now. And what feels like the same moment to you might not be the same moment to me. If we are far apart or moving differently, it's almost unsettling to realize there is no single, universal present. We live in a patchwork of nows, stitched together loosely, sometimes drifting apart. Einstein once said that the distinction between past, present, and future is only a stubborn illusion. What he meant wasn't that time is meaningless, but that the way we think of it, a single, global heartbeat, doesn't match the truth of the universe. Time is personal. It belongs to the path you take through space-time. This understanding didn't come to Einstein all at once. He built it piece by piece, starting with special relativity in 1905, which showed how motion changes time, and then expanding it into general relativity in 1915, which wove in the role of gravity. It took years of thinking, of imagining light beams, of chasing thought experiments, as if they were real. One of those thought experiments was imagining a clock made of light. Picture two mirrors facing each other, with a single photon, a particle of light, bouncing between them. For someone holding the clock, the photon goes straight up and down. But if that clock is moving very fast, someone watching from outside will see the photon take a longer diagonal path. Since light always travels at the same speed, the photon takes more time to complete its journey, which means the moving clock ticks slower. That's time dilation, seen not in equations, but in the dance of light. The beauty of relativity is that it's not just theory, it's been proven again and again. Experiments have flown atomic clocks on airplanes around the world and compared them to clocks left on the ground. The travelling clocks came back slightly out of sync, exactly as relativity predicted. Satellites in orbit run on a rhythm that must be corrected for both their speed and their height above Earth's surface. Even the signals from deep space probes carry the imprint of relativistic effects. And yet, for most of us, these differences in time are invisible. We live our days as if time is the same for all. We meet for coffee at 10, catch a train at 5, celebrate a new year together at midnight. Relativity is always there, but it whispers so quietly that we don't notice unless we look for it. The truth is that the flow of time is not something you can feel with your skin. Standing on a mountaintop, you don't sense that your seconds are passing slightly faster than they are for someone at sea level. Riding in an airplane, you don't feel your clock slowing by a billionth of a second, but the universe feels it. The fabric of space-time is always responding to your movement, to the mass beneath your feet, to the gravity that cradles you. And so, when we ask, does time flow the same everywhere? Einstein's answer is gentle but firm. Number. It flows differently, and that difference is written into the very shape of reality. In the next part of our journey, we'll slow down even more and look closely at one of these effects, how gravity itself can stretch time like honey flowing more slowly in the depths of a jar than at the surface. Because to understand time's variations, we must listen to the pull of the earth and the way it tugs on the seconds of our lives. If you have ever stood at the edge of a deep valley and felt the air press a little heavier on your skin, you've already met the quiet hand of gravity. It's not just a force that pulls apples down from trees or keeps your feet anchored to the earth. It also reaches into something far more subtle, the ticking of time itself. Einstein's theory of general relativity told us that gravity is not a simple invisible tug. It's the bending of space-time, caused by the presence of mass. And when space-time bends, it bends time as well as space. This means that gravity doesn't just keep you on the ground, it also changes how quickly your seconds pass. The rule is gentle but absolute. The stronger the pull of gravity, the slower time flows. At sea level, where the Earth's gravity is slightly stronger, time moves just a fraction more slowly than it does high on a mountain peak. It's not something you can feel in your bones, and no heartbeat will betray it. But an atomic clock will. Those precise instruments have measured the difference. Tiny, yes, but undeniable. To picture it, imagine a river of honey. In the shallows, it flows freely, moving quickly toward its destination. But in the deepest part of the jar, where the honey is thickest, it moves more slowly. Gravity works like that on time. The deeper you are in a gravity well, whether that's near the surface of Earth or closer to a massive planet or star, the slower your seconds trickle by. It's not just an earthbound curiosity. Out in the cosmos, this effect becomes far more dramatic. Near a neutron star, a teaspoon of which can weigh billions of tons, time would run so slowly that an hour there might equal days or weeks far away. And near the edge of a black hole, gravity's pull is so intense, that time, as seen from outside, seems to nearly stop altogether. This is not fantasy. It's the mathematics of space-time, played out in the most extreme conditions imaginable. But back here on Earth, gravity's effect on time is modest, yet still important. When scientists synchronize clocks for GPS satellites orbiting above us, they must account for two opposing forces. The satellites are higher up, where gravity is weaker, so their clocks tick faster than those on the ground. But they are also moving quickly through space, and motion, as we've learned, slows time down. These two effects almost cancel each other out. Almost, but not entirely. Engineers correct for the tiny difference every day, ensuring that when your phone says, "You're standing on a street corner," it really means it. We've measured this on smaller scales too. In a famous experiment, scientists placed two atomic clocks at different heights in a building. The one just a few floors higher ticked slightly faster than the one closer to the ground. The difference was measured in nanoseconds, but it was there, a whisper of relativity, playing out quietly in the space of a stairwell. The poetry of it is hard to ignore. It means that if you lived your whole life on a mountain, you would experience a few more moments than someone who lived at sea level. The gift would be small, fractions of a second over a lifetime, but it's there, hidden in the way gravity strokes the flow of time. And it works in reverse too. Spend enough time deeper down, say, in a submarine for decades, and your clock would run a touch slower than the clocks on the surface. In that sense, gravity is like a quiet editor, stretching or compressing the story of your life, depending on where you stand. What's beautiful, and maybe a little humbling, is that this bending of time isn't something we invented. We simply discovered it. Like finding a hidden pattern in a piece of music you've heard your whole life. Time was never flowing the same everywhere. We just hadn't listened closely enough to notice. You can even imagine the Earth as a layered timekeeper. At its molten core, time flows the slowest. As you rise through the mantle and crust, seconds begin to pass more quickly. At the highest mountain peaks, time flows the fastest it can on our planet, still slower than in the emptiness of deep space, but freer than in the depths below. This gentle stretching and squeezing of time has consequences for more than just GPS. It's a reminder that every clock, whether it's on your wrist, in a laboratory, or inside your own body, is tied to the landscape around it. Your seconds are not universal. They belong to the place you are standing. And yet, we don't live in fear of these differences. We don't feel cheated that someone in the mountains is getting more time than we are. The truth is, our human lives are too short and too beautifully busy for these tiny shifts to matter in our daily routines. What they do offer, though, is perspective, the realization that time is not an absolute, but a local story. The deeper lesson is this: when you look up at the stars, you're not just looking across distance, you're looking across time and the way it flows differently in different places. A star's light may have left when time was ticking differently there than it is here. The very beams we see are shaped by the gravity wells they've passed through, each one bending their journey just a little. So, when we ask if time flows the same everywhere, gravity answers in a low, patient voice. Number. I hold some moments longer and let others slip past more freely. I shape the river, but I do not stop it. In the next part of our journey, we'll leave the mountains and valleys and step into the world of motion, the other great sculptor of time, because speed, just like gravity, has its own way of bending the clock. There is something about speed that thrills the human heart. The rush of a train cutting through the night, the quiet hum of an airplane climbing through clouds, the imagined leap of a spacecraft sailing toward another world. We think of speed as a matter of distance and motion, how far, how fast, but Einstein showed us that speed touches something deeper. It changes the very flow of time. This idea first emerged from his theory of special relativity, written in 1905, and it rests on one simple, beautiful truth. The speed of light in a vacuum is always the same. No matter how fast you're moving toward it, or away from it, the light greets you at exactly the same pace, about 299,792 kilometers per second. To keep this rule unbroken, the universe adjusts something else: time itself. Imagine you are holding a clock, but instead of hands and numbers, it keeps time with a single beam of light, bouncing between two mirrors. For you, standing still, the beam travels up and down, in a straight line. But to someone watching you zoom past at great speed, that same beam appears to take a longer, slanted path between the mirrors. And since the speed of light cannot change, the only way for this to work is for the moving clock to tick more slowly. This is called time dilation, a slowing of time for objects in motion, relative to those at rest. It's not a trick of perception, not an illusion. It's a measurable, physical truth. In everyday life, the effect is tiny. When you take a plane from one city to another, your personal clock runs a few billionths of a second, slower than the clock of someone who stayed home. But in the realm of high speeds, close to the speed of light, this effect becomes enormous. A traveler moving at 90% the speed of light would experience time passing about twice as slowly as someone at rest. At 99.9%, the difference would be staggering. Years might pass for the stationary observer, while only days pass for the traveler. This is not only theory. We see it in the lives of subatomic particles. Muons, for example, are created when cosmic rays hit Earth's atmosphere. They decay in millionths of a second, so quickly that, without time dilation, they shouldn't survive the journey to the ground. And yet they do, because, from our perspective, their internal clocks are slowed by their high speed. It happens in technology too. The atomic clocks aboard GPS satellites are affected by both their speed and the weaker gravity they experience high above Earth. Their motion slows their ticking slightly, while their altitude speeds it up. Two opposing effects, both predicted by relativity, both measured and corrected for daily. So your phone can guide you home without error. The poetry of this is inescapable. Motion bends time. Run, fly, or sail fast enough, and you are stretching the seconds themselves. Every step, every heartbeat, is gently slowed compared to those left behind. It's as if the universe is saying, if you wish to hurry through space, I will make you linger in time. And there is a strange symmetry here. In segment 3, we saw how gravity slows time down. When you are deep in its pull, speed does something similar, but for a different reason. Gravity bends time because it bends space-time. Speed bends time because it insists on keeping the speed of light the same for everyone, and the only way to do that is to let moving clocks tick more slowly. If you think about it long enough, it begins to feel almost generous. Time dilation is the universe's way of keeping its promises, making sure that the rules hold, no matter where you are or how you move. And perhaps the most haunting example of all comes from a thought experiment, often called the twin paradox. Imagine two twins. One stays on Earth, the other boards a spaceship and travels close to the speed of light to a distant star and back. When the traveling twin returns, less time will have passed for them than for the twin who stayed home. The traveler will have aged less. It's not a trick of clocks. It's reality. Their cells, their thoughts, their very experience of life will have been slowed by their journey. It's strange to imagine that you could leave home and return to find the world older than you are, that loved ones have aged while you have not, that events you missed are now part of history, irretrievable. In this way, time dilation is both a gift and a thief, granting you more of your own moments, but stealing them from the shared rhythm of others. But here, in our gentle earthbound lives, these differences are invisible. A runner's seconds and a sleeper's seconds tick almost identically. The hum of the city and the quiet of the countryside do not carry clocks in different tempos. We can hear with our ears. Speed's hand on the flow of time is so soft here that it takes the most sensitive instruments to feel it. And maybe that's why this truth is so peaceful to think about at night, because it reminds us that time is not absolute. It is personal, elastic, willing to bend for the path you take. Your seconds belong to your journey, and they are yours alone. So the next time you see a plane's lights tracing across the night sky, or watch a train rush past in the distance, you might remember those travelers are living in a slightly different flow of time than you are right now. Their clocks and their hearts are ticking just a little more slowly. The quiet work of motion, carving tiny ripples into the river of time. In the next part of our journey, we'll bring these threads together, gravity and motion, and see how they shape time, not just for individuals, but for the entire cosmos. Because in a universe full of stars and planets, black holes and galaxies, time is never a single, steady beat. It's a symphony with many tempos, all playing at once. When you look up at the night sky, it can feel like you're staring into a single moment. Stars frozen in place, planets tracing their slow arcs, the moon holding her glow. But in truth, the sky is a room full of clocks, each ticking to its own rhythm, each measuring time differently. Some of these clocks are slow, weighed down by the immense pull of gravity. Others tick more quickly, drifting free in the lighter grasp of space. Motion plays its part too, slowing time for the wanderers, who race through the cosmos at tremendous speeds. Think first of a clock deep inside a galaxy's heart. There, a supermassive black hole weighs millions, sometimes billions, all of times more than our Sunday. Its gravity warps space-time so severely that seconds near its event horizon crawl compared to those far away. For someone orbiting close to such a black hole, time would stretch. Minutes for them could be centuries for us. In the black hole's embrace, time becomes almost syrup, thick and resistant, as though the universe itself is reluctant to let moments go. Now, picture a clock in the quiet space between galaxies, where gravity is faint and motion is slow. Here, time runs more freely. An identical clock set in this emptiness would tick faster than its twin on Earth, unburdened by strong gravitational fields or great speeds. This isn't just a curiosity. It means that the cosmos does not share a single, universal now. What we call the present is woven differently depending on where you are. If you could line up all these cosmic clocks, one on a mountain, one in orbit, one on a distant moon, one skimming the edge of a black hole, you would see their hands, no longer in step. They're all telling the truth, but not the same truth. Astronomers must take this into account when they measure the universe. Signals from pulsars, rotating neutron stars that beam radio waves, with perfect regularity, must be corrected for the gravitational fields and speeds they've experienced on their way to us. A pulse that began its journey in a strong gravity well may arrive slightly out of sync with one sent from a lighter place, and yet both were perfectly on time where they began. Even light itself can be thought of as carrying a kind of clock. It travels unchanged at the speed of light, but its color, its frequency, can shift depending on the gravity and motion it's passed through. This is why astronomers talk about gravitational redshift. Clocks deep in gravity's pull send out light that arrives stretched. It ticks farther apart. It's as though the light has carried the memory of slower time across the darkness of space. Here on Earth, we're cushioned from the extremes of this. Our planet's gravity is steady, our motion around the sun predictable. But even here, the idea of a single universal time is an illusion. The GPS satellites overhead keep their own versions of time, corrected every moment to align with ours. And even two people in different altitudes live in subtly different tempos, their seconds not perfectly matching. It's tempting to think this makes the universe a messy, unsynchronized place. But in a way, it's the opposite. This dance of different clocks is part of the design. Einstein's relativity doesn't break the harmony, it is the harmony. The rhythm of the cosmos is not that of a single drummer, but of countless instruments, each playing its part in a grand shifting composition. Imagine now, you are drifting far from Earth, past the pull of our sun, past the sway of our galaxy's spiral arms. You carry with you an atomic clock. It's ticking, steady and precise. Out here, where gravity is weak, and your speed is gentle, your seconds lengthen ever so slightly. Back home, centuries from now, your clock will show a different history than the ones that stayed behind. Neither is wrong. Each is telling the story of the place it has been. And perhaps this is the quiet wonder in all of this. Time is local. It is not an ocean with the same tide everywhere, but a series of streams, each shaped by the landscape it flows through. Gravity can slow it. Speed can stretch it. And in the vastness of the universe, the differences can grow into lifetimes. This means that when you look at a distant galaxy, you are not just looking across millions of light years of space. You are looking across millions of years of different time. Its stars have been aging in their own rhythm, its planets spinning in their own tempo, and the light now, reaching your eyes, is a message from a clock that was never ticking in perfect unison with yours. The idea can feel dizzying, but there's comfort in it too. It means our own lives are part of a much larger story, one where time is not a single thread, but a vast tapestry woven from the many paces of the cosmos. Some stitches are slow and deliberate, others quick and fleeting, but together they form the fabric of reality. And here, in the stillness of the night, as you rest and listen, you might imagine yourself as one more clock in this vast collection. Your seconds may be shaped by Earth's pull and your gentle motion through space, but they are yours, part of your place in the universe. In the next segment, we'll take this cosmic perspective and bring it closer to home to see how time can bend, not just across light years, but in the spaces and moments we live every day. Because even here, in the warmth of our own lives, time can flow differently than we expect. You don't have to be orbiting a black hole or racing through the galaxy to feel the touch of relativity. It's here, quietly woven into the everyday, affecting you in ways so small you would never notice without the right kind of clock. Imagine you are standing at the base of a tall building. Someone else is at the very top. You both start perfectly synchronized watches. By the time the day ends, their watch will be running a fraction of a second faster than yours. Why? Because they are ever so slightly farther from Earth's center, and its gravitational pull. Gravity slows time, and in the weaker gravity higher up, seconds slip by a little more quickly. The difference is impossibly tiny for a human to sense, but for the machines we rely on, it's enough to matter. GPS satellites orbit high above us, carrying atomic clocks so precise, they could lose or gain less than a billionth of a second in a day. Yet without correcting for both the weaker gravity up there, which speeds their ticking, and their high orbital speed, which slows it down, our navigation systems would be useless in minutes. Your phone's map would drift hundreds of meters off course. By the time you walk to the corner store, even in the kitchen, relativity has a seat at the table. If you could bake bread on top of Mount Everest and compare it to the same recipe cooked at sea level, the difference in gravitational time dilation would technically be there. Microscopic, unmeasurable by taste, but present all the same. Relativity also lives in the way we synchronize time across continents. Signals sent to coordinate stock trades, to measure seismic events, or to link observatories into one giant telescope must account for the fact that no two places on Earth share exactly the same tempo. A clock in Chile is not ticking in perfect unison with one in Hawaii or Italy. Gravity and motion conspire to make them each their own. Even your own body carries tiny echoes of these effects. Your head lives in slightly weaker gravity than your feet, and so, if we follow the math, the top of you is aging a little faster than the bottom. In the span of a lifetime, the difference is too small to feel, but it is real, a reminder that every part of us has its own relationship with time. When physicists measure these shifts in the lab, they often use two incredibly precise atomic clocks. Place them side by side, and they tick together. Raise one just a few centimeters higher, and the one above begins to run faster. It's as if time itself notices the change instantly, adjusting its flow to match the new position. And this is where relativity turns from abstract to intimate, because while these effects are minuscule here on Earth, they whisper the same truth that governs black holes, neutron stars, and the edges of the universe. Time is not absolute. It bends, stretches, and shapes itself around motion and gravity. Wherever you are, we live our lives, trusting in the steady tick of the clock, the predictable turn of the calendar. And for our purposes, that works. Seconds, minutes, hours are as reliable as we need them to be. But deep down, underneath our schedules and habits, is a truth both humbling and beautiful. Your seconds are not quite the same as mine. They belong to your place, your motion, your moment in the cosmos. It's easy to forget that relativity touches us here, because the scale is so small. We think of it as something that happens to astronauts or distant stars, but it is here, in the phone in your hand, in the planes in the sky, in the satellites circling overhead, and in the quiet difference between your head and your feet. And maybe that's why this everyday relativity feels almost like poetry. The same rules that keep a spacecraft's time in check also shape the seconds of a morning walk. The physics that bends the life of a star also lives in the subtle beat of your own heart. So tonight, as you drift into sleep, remember that you are already part of the grand experiment. You carry your own clock, unique to you, marking moments that are yours alone. Every step you take, every hill you climb, every breath you draw is being measured in a way no one else will experience exactly the same. In the next segment, we'll explore what happens when these different flows of time meet, when the fast and the slow try to share the same moment. Because in a universe with so many tempos, synchronizing is never as simple as it seems. In a perfect world, all clocks would agree. The tick of a second here would match perfectly with the tick of a second there, and time could be passed from one place to another without the slightest distortion. But we don't live in that kind of world. We live in a universe where gravity tugs unevenly, where speed stretches moments, and where no two locations experience time in quite the same way. Bringing these different tempos into alignment is both an art and a science, a quiet choreography played out between machines, observatories, and even the satellites far above our heads. Consider the vast network of timekeepers that run our modern lives. There are atomic clocks buried deep underground, in laboratories shielded from temperature shifts, and others that circle the Earth in satellites, whispering timestamps down to our devices. They form a global conversation, comparing ticks and tocks, making corrections in billionths of a second. Each clock is aware, in its own mechanical way, that its reality is not the same as the others. The ones higher up feel a lighter gravity and tick faster. The ones in motion have their seconds stretched by speed, and the ones closer to Earth's center tick just a touch more slowly. This is where synchronization becomes a delicate act. Physicists and engineers must constantly adjust these clocks, so they agree on what now means. Even though their raw measurements disagree, they use relativity itself as a kind of translator, accounting for the warps in time caused by position and velocity. It's not unlike tuning an orchestra. Each instrument, each clock, is perfectly capable of keeping its own tempo, but to make music together, they must listen, adapt, and find a shared rhythm. In space exploration, this harmony is essential. When a spacecraft sends a signal from Mars, engineers need to know the exact time it left and the exact time it arrives. But Mars is moving at its own pace, through the sun's gravity, and the clocks on Earth are moving differently. Without accounting for these mismatches, we couldn't steer a rover across alien terrain or land a probe on a distant moon. Even here, on Earth, synchronization holds the threads of our daily life together. Financial markets rely on timestamps so precise that a tiny error could mean millions gained or lost. Global communication systems. We need to agree on time down to microseconds, so that data packets arrive in order, and the world's scientific collaborations, like the network of telescopes that captured the first image of a black hole, depend on merging observations, taken in slightly different nows, into a single, coherent picture. In truth, every attempt to synchronize time is a small act of reconciliation. It's an admission that there is no single perfect clock in the sky, ticking for all of us. Instead, there are countless local times, each valid, each shaped by the forces and motions around it. When we synchronize, we're not erasing those differences, we're building a bridge between them. And there is something quietly beautiful in that. Think of two people walking side by side, one taking slightly longer steps than the other. They adjust, without thinking, a matching pace so they can share the road. That is what our clocks do. When they agree on a time, they're not suddenly identical. They're simply in step for as long as they need to be. There are moments, too, when synchronization becomes a matter of survival. In navigation at sea, in the early days before satellites, ships depended on precise timekeeping to know where they were. A chronometer that ran fast or slow could send a vessel hundreds of miles off course. Sailors learned to trust not a single clock, but a routine of checks and recalibrations, matching their measurements to the stars. Even then, they were unknowingly working with a universe where time's tempo shifted with every tide and latitude. Today, we've built systems so accurate that we rarely think about them. Your phone updates its clock automatically. Airplanes cross time zones, without passengers ever noticing. The careful handshakes happening between ground stations, satellites, and cockpit instruments. But behind the curtain, relativity is still there, still bending seconds, still making sure that every tempo, from the top of a mountain to the belly of the ocean, is brought into alignment. And if you listen closely, there's a metaphor waiting in this. Our lives too are lived in different tempos. We wake and rest at different hours. We move quickly through some seasons, slowly through others. We carry our own rhythms, shaped by where we are and what we've lived through. Yet somehow, we still find ways to meet each other in a shared moment, to align our days for a conversation, a meal, a quiet walk. Synchronizing time in the cosmos is not about forcing sameness. It's about respecting difference while finding common ground. It's the quiet work of keeping the universe in conversation with itself so that messages can cross vast distances, so that stories can be told, so that we can feel connected, even when our moments are not identical. In the next segment, we'll explore what happens when we try to measure time on the larger scales, not seconds or days, but cosmic ages. Because in a universe where clocks disagree, even the age of the stars depends on where you stand. When you look up at the night sky, you are not seeing now. You are seeing the past, a light that has traveled for years, centuries, sometimes millions of years, before finding your eyes. A star that twinkles above you tonight may have already lived and died, its final light still making the journey here. In the language of the cosmos, time is always written in delay. Every point of light in the sky is a message sent long ago. But how do we measure ages? In a universe where time flows differently in different places. On Earth, we count our days by the turning of the planet, our years by its trip around the Sunday. But in deep space, where there is no sunrise and sunset to guide us, we need other clocks, clocks that are not bound to a single world. For stars, one of the most telling clocks is the way they burn their fuel. A star's brightness and colour can reveal how far it is along its life cycle. Hot, young stars blaze blue-white, spending their fuel recklessly, burning through their hydrogen in only a few million years. Cooler, older stars glow red, settling into a slower, steadier rhythm that can last billions of years. By comparing these traits to what we know from physics, astronomers can guess a star's age, the way a tree's rings reveal its seasons. But here's where relativity steps in again. If you were hovering close to a massive star, time would pass more slowly for you than for someone far away from it. From your perspective, the star's clock would seem to tick at its natural pace. From theirs, the same star's life might appear slightly sped up. The star's age is not one fixed number. It is a value that shifts depending on the observer's frame. And yet, despite these differences, we have built a kind of consensus time for the cosmos. We speak of the sun as being about 4.6 billion years old, of the universe itself as 13.8 billion years old. These numbers are the result of careful translation between different clocks, folding in the corrections for gravity, motion, and the stretching of space itself. This stretching, the expansion of the universe, is perhaps the most profound time shaper of all. As the universe expands, the light traveling through it is stretched into longer wavelengths, a process called redshift. When we measure this shift, we are reading how much time has passed since that light was emitted. It is as if every photon carries a little diary entry, its pages stretched thinner and thinner as the universe pulls it along. To measure truly cosmic ages, we look for the oldest light there is, the cosmic microwave background, a faint afterglow from when the universe was just 380,000 years old. This light has been traveling for over 13 billion years, cooled and stretched by expansion, but still carrying the imprint of that early moment. By studying its patterns, we are, in a sense, peering into the baby album of the cosmos. On smaller, though still enormous scales, we can use the life cycles of star clusters as galactic calendars. Globular clusters, those dense, ancient gatherings of stars, are among the oldest known objects in the universe, some over 12 billion years old. Their shared ages tell us that they formed early in the life of the galaxy, before its spiral arms had fully wound into place. They are like old towns in the countryside, their architecture unchanged, carrying the memory of an earlier time. Yet, the act of measuring age on a cosmic scale is never purely objective. Every measurement is filtered through the way we experience time here on Earth. In our little pocket of gravity and speed, we anchor our cosmic clocks to our own, knowing that somewhere else, someone else, if they existed, would get a different number. And maybe that's the humbling beauty of it. In a universe so vast that it takes light billions of years to cross it, we can still weave a shared story of its history. We can agree on a timeline, not because it is the only truth, but because it is a truth, carefully translated between countless frames of reference. Think of an orchestra again, but this time spread across light years. Each section plays in its own tempo, but with enough patience, enough listening, you can layer the sounds into a single, beautiful piece. That's what we've done with cosmic time, taken the different rhythms of stars, galaxies, and the expansion of space itself, and shaped them into a single, coherent melody of the universe's life. And while the numbers may be vast, billions upon billions of years, they are also intimate, because the atoms in your body were forged in stars that lived and died long before the sun was born. When we measure the age of a star, we are, in some small way, measuring a chapter in our own history. So, the next time you look up, remember, you are looking into time itself. The stars are not just lights in the dark. They are clocks, each keeping time in its own way, each carrying a story from a different moment in the universe's long, ever-shifting history. In the next segment, we'll bring these ideas closer to home. We'll see how this cosmic dance of time touches the everyday flow we live in, and how even here, on our little blue planet, time can be a slippery, beautiful thing to hold. Close your eyes and think of the word now. It feels simple, doesn't it? A single moment you're living in, the breath you're taking, the sound you're hearing, the light touching your skin. But now is slippery. It's already changing by the time you notice it. The moment you say, "This is now," it has already become the past, and the next moment has arrived without asking. In our everyday lives, we treat now as something shared. We meet friends at a certain time, watch the same sunset, celebrate the same turning of the year. We trust that our clocks agree well enough to keep our lives in sync. But physics tells a more complicated story. There is no single universal now. Imagine two people separated by light years. If one sends a signal, the other won't receive it until much later. Their nows are not the same, because the information connecting them must travel through space at a finite speed. Even here on Earth, your now is not exactly the same as someone else's on the other side of the planet. The difference is too small to notice, but it exists, a whisper of relativity, woven into our days. Einstein's theory tells us that what you call now depends on where you are and how you're moving. Two observers, each traveling at different speeds, or sitting in different pockets of gravity, will slice the timeline of the universe differently. Events you think are happening now might already be the past, or still be in the future, for someone else. This is called the relativity of simultaneity, a mouthful of a term, for something both simple and strange. There is no cosmic master clock, telling everyone the same moment. Instead, now is a local experience, an agreement between you and your surroundings, not a decree from the universe. And yet, we humans are creatures of shared moments. We've built cities, traditions, and entire histories around the idea that we can point to the same now. We make it work because the differences in our everyday world are so tiny that they can be ignored. Unless you're navigating a spacecraft or syncing atomic clocks across continents, holding on to now is also a challenge for the mind. Your brain does not register the world instantly. It takes time to process sound, light, touch. When you hear a clap, your ears send signals to your brain, which interprets them a fraction of a second later. When you see lightning, your eyes do the same with light. Your now is always a tiny reconstruction of the past, stitched together so smoothly, you never notice the lag. And there's another twist. Your sense of now can stretch or shrink. In moments of danger, your brain can flood with adrenaline, slowing your perception, making each second feel like a long, drawn-out instant. In moments of joy or deep focus, time can seem to vanish, hours slipping past without a trace. Your personal now is elastic, woven from attention and memory, as much as from the ticking of a clock. There's a paradox here. We long to capture the present, to hold it still, and yet it's the movement of time that gives the present its meaning. A photograph freezes a smile, but it is the memory of what came before and after that makes it real. If the present never changed, it would no longer feel alive. Physics, too, has its way of acknowledging this. Some scientists describe the universe as a block of space-time, where all moments, past, present, future, exist at once. In this view, now is just the slice we happen to experience, moving through the block, like a spotlight in the dark. Others see time as a river, flowing forward, and carrying us along, its current shaped by gravity, speed, and energy. In either case, the present is not an absolute thing. It's a relationship between you, your motion, and the universe around you. And perhaps this is where the slipperiness of now becomes less a frustration and more a gift. If the present cannot be held, then it must be lived. We meet each moment as it arrives, knowing it will pass, and in that passing, it will make room for the next. Think about how you've experienced today. The moment you woke, the taste of a meal, the sound of a friend's voice, they all happened in different nows that have slipped away, but they leave behind a shape, a day uniquely yours. Tomorrow's now will feel different again, and the day after that, and so on, as long as your clock is ticking. So, maybe now is not something to pin down, but something to visit, over and over, like a room you enter briefly, each time finding it changed. We can't freeze it, but we can stand in it fully, letting the light and sound and air wrap around us. Before we step forward, and if, somewhere far away, another being is also standing in their own now, then the universe holds two moments at once, different, yet part of the same vast fabric. In that sense, now is both personal and shared, fleeting and eternal. In the next segment, we'll close our journey by stepping back from clocks and equations. We'll ask why all of this matters, why the way time flows, uneven and relative, still feels like one of the most mysterious and magical aspects of the universe we live in. If you've ever stood by the shore and watched the ocean, you've seen a rhythm that feels eternal, waves rising and falling, each one different, each one part of the same endless movement. Time, too, has its tides. It flows differently in different places, but it flows nonetheless. It can be stretched by gravity, slowed by speed, distorted by perspective, Yet the movement is always there, and like the ocean, it leaves patterns in its passing, shorelines carved over millennia, memories etched into hearts. Why does the way time flows matter? Because it shapes the very structure of reality. It decides what we can see, what we can change, what we can remember. Without time's current, the universe would be a still image, beautiful perhaps, but without story. Relativity teaches us that there is no single, universal clock ticking above us all. Instead, there are countless local times, each one as valid as the next. The clock on a satellite, the clock in a mountaintop observatory, the clock in your own heartbeat, they each mark the passage of time, slightly differently. And yet, our lives are not chaos. We have learned to translate, to synchronize, to create a shared rhythm, even across the differences. This matters because it means that the world you experience is yours alone, a timeline stitched together from where you are and how you move. It also means that the stories of others are stitched from different threads. We are all walking through time, but never in exactly the same way. There is something deeply human about wanting to know this. We count days, we mark anniversaries, we keep records not because we can control time, but because we want to witness it. We want to be part of its flow, even as it carries us somewhere we cannot yet see. The tides of time also connect the smallest moments to the largest scales imaginable. A second of laughter with a friend, and the 13.8 billion years of the universe's history. Both live in the same fabric. The ticking of a kitchen clock and the decay of a distant star are bound by the same laws, though they feel worlds apart. When you begin to notice time's different tempos, you may also begin to notice its beauty. The slow pull of seasons, the way shadows stretch as the day ages, the pause before a word is spoken. All of these are time's fingerprints, tiny signatures on the surface of your life. And perhaps the most important thing to realize is that the flow of time gives meaning to change. It is the reason flowers bloom and wither, why mountains rise and erode, why we grow, why we remember. If time did not flow, nothing could become. Even the unevenness of time, its tendency to run differently, for a traveler on a spaceship, or for light climbing out of a deep gravity well, is not an imperfection. It is a feature, a reminder that time is not a rigid ruler, but a living dimension, intertwined with space and matter. It bends, it flexes, and in doing so, it makes the universe possible. So, why does time feel so mysterious to us? Perhaps because we are both in it and made of it. We are not separate from time's river. We are drops within it, flowing along, carrying traces of where we've been, headed toward a horizon we cannot yet see. And in this vastness, in this endless variation of moments, there is comfort. Because no matter where you are, no matter how differently your clock may tick, you are always within the tide. You are always part of the movement, part of the story. If you close your eyes and listen, you might even feel it, not as a ticking, not as numbers, but as a soft, steady current beneath everything. It is there in your breathing, in the faint hum of the world around you, in the light that took minutes or centuries to reach you. And so, as we end this journey, we return to where we began, with a question about time and a reminder that the answer is both scientific and deeply personal. Time does not flow the same everywhere, but everywhere, time flows. It is the tide that carries the universe forward, the rhythm that writes every story, the quiet music playing beneath all things. Now, my friend, you've been walking through many moments with me tonight. You've traveled from the clocks in your pocket to the edges of the universe's first light. And here we are, back in this single moment we call now. If you'd like, you can let this be your resting place. Find a comfortable position, close your eyes, breathe slowly, feel the gentle tide of time as it moves through you. Let the stories we've explored become soft echoes in your mind. The music will carry you now, a calm current, to drift along until sleep finds you. The night is wide. The tide is steady. You are safe to rest. Good night.